You may have observed that a drop of blood forms a hump on a horizontal. A drop of mercury forms a near perfect sphere and can be rolled just like a steel ball over a smooth surface. Water dew hang from the leaves of trees. A soap bubble released into air forms a spherical shape. All these observances are consequences of surface tension. Let's understand how surface tension in liquid works. Let's consider a bottle filled with liquid water. At microscopic level, water molecules apply attraction towards each other, and this type of attraction between similar molecules is known as cohesion. At the liquid surface level, there are air or gas molecules which also attracts the water molecules near the liquid surface. This type of attraction between dissimilar molecules is known as adhesion. Now the attractive forces applied on the interior water molecules by the surrounding molecules balance each other because of symmetry. But the attractive forces acting on the water molecules at the surface are not symmetric, and the attractive forces applied by the gas molecules above are usually very small. This causes a net attractive force on the molecules at the liquid surface, which tends to pull the molecules on the surface towards the interior of the liquid and cause a tension on the surface of the liquid. This force is balanced by the repulsive forces from the molecules below the surface that are being compressed. The resulting compression effect causes the liquid to minimize its surface area. This is the reason for the tendency of the liquid droplets to attain a spherical shape, which has the minimum surface area for a given volume. You can observe this curved surface on a glass completely filled with water. Also, you may have seen small needle can float on water, and some insects can even walk on water. These phenomena are again made possible by surface tension that balances the weight of these objects. The surface tension varies greatly from substance to substance. For example, at 20 degrees Celsius, the surface tension of water surrounded by atmospheric air is 0.073 Newton per meter, and for mercury it is 0.44 Newton per meter. This is because mercury is a metal, and the bonds connecting its molecules are metallic bonds, which are considerably stronger than the hydrogen bonds between the water molecules. The table shows surface tension values of some liquids. Let's look at some factors affecting the surface tension of a liquid. First, temperature. The surface tension of a liquid in general decreases with temperature and becomes zero at a critical point. The critical point is the temperature above which there is no distinct liquid-vapor interface. This table shows the decrease in surface tension of water with rise in temperature. The surface tension of a liquid can be changed considerably by adding impurities, like a soap or detergent in water. Soap molecules consist of a charged head and an uncharged tail. As we know, a water molecule forms hydrogen bond with other water molecule. When soap is added to the water, the negatively charged oxygen in a water molecule will be attracted to the head of the soap molecule, and the hydrogen bond with the water molecules tend to break. This lowers the surface tension of water and enable it to penetrate through the small openings between the fibers for more effective washing. Surface tension causes water drop to appear as a spherical drop. The water molecules near the water-air interface are attracted by the adjacent molecules on their side, which causes a tension on the interface. These attraction forces on either side of a molecule are balanced. Then we have internal molecules which attracts the surface water molecules from below. This causes minimization of surface area and creates a net upward force on the water molecules at the surface. Now since area is decreased and the number of molecules remains same, this causes a significant pressure inside the droplet. There is pressure P in inside the droplet and pressure P out, or air pressure outside the droplet. A curved interface indicates a pressure difference across the interface with pressure being higher on the concave side or the pressure inside the droplet. Otherwise, if pressure is higher outside the droplet than inside, then droplet will collapse. This is similar to a balloon filled with air. When air is released, the higher air pressure inside the balloon forces it to fly. The excess pressure inside a spherical droplet can be determined by slicing the droplet into two halves having radius r. The two droplet halves separated from each other will be attracting each other along the circumference of their cross section. So the force due to surface tension can be written as surface tension multiplied by the length along which it acts, which is 2 pi r. The pressure P out is applying force on the interface in the direction similar to the surface tension. So we can write force due to P out as P out into area pi r square. The pressure P in is applying force on the interface in the direction opposite to the surface tension. So we can write force due to P in as P in into area pi r square. On rearranging we get now P in minus P out is the excess pressure delta P, and the force due to this excess pressure is in the direction opposite to the surface tension. Thus we can write sigma s into 2 pi r equal to pi r square into delta P droplet. On rearranging, finally we get delta P droplet as 2 sigma by r. From this expression we can see that the pressure drop across the droplet depends on the size of the droplet. Now let's see the case for a soap bubble. The surface of a soap bubble consists of two layers of soap molecules with their tails pointing out. Between the two surfaces, water molecules are trapped. So for a soap bubble there are two surfaces on which surface tension acts. The gap between these two surfaces is very less, so we can assume the radius for both the surfaces to be capital R. Thus the force due to surface tension is double that of water droplet, and the force due to pressure across the interface remains the same. Finally, on rearranging we get delta P for a bubble equal to 4 sigma s by r. Now let's see how to find pressure difference in case of a liquid drop having an arbitrary curved surface. Consider a small surface element of this drop ABCD. This is made up of two sets of parallel lines AB and DC, which are equal to x units, and AD and BC equal to y units. Here AB and DC have different curvature than AD and BC. So we can say this element has two sets of curvature in two different planes. Let's say the radius of curvature for this element as R1 in the direction of x-axis, that is with respect to parallel lines AB and DC. Now if we stretch this element by delta z units, we get A dash, B dash, C dash, D dash as the stretched element, where A dash, B dash and D dash, C dash equal to x plus delta x units, and A dash, D dash and B dash, C dash equal to y plus delta y units. So we can write R1 by R1 plus delta z equal to x by x plus delta x. Further we can write R1 by delta z equal to x by delta x. Similarly, the radius of curvature for this element is R2 in the direction of y-axis, that is with respect to parallel lines AD and BC. So we can write R2 by R2 plus delta z is equal to y by y plus delta y. Further we can write R2 by delta z equal to y by delta y. Let's consider a pressure difference delta P between outer and inner side of surface element ABCD, which causes the surface element to stretch. The pressure delta P gives rise to a force. Work done due to delta P is delta P into x into y, which is the force on curved surface area xy due to delta P into delta z. The corresponding work due to surface tension is surface tension multiplied by change in area, which is given as sigma s into x plus delta x into y plus delta y minus original area xy. On simplifying, xy cancel out, and delta x into delta y is very small value, so we can neglect that. Finally we get sigma s into x delta y plus y into delta x. Now if we equate these two works, we get delta p is equal to sigma s by delta z into y delta y by y plus delta x by x. On simplification, we can write delta p is equal to sigma s by delta z into delta z by r2 plus delta z by r1, and finally we get delta p is equal to sigma s into 1 by r2 plus 1 by r1. This equation is known as Young's Laplace equation. If we put r1 and r2 equal to r in this equation, then we will get the expression of excess pressure for a spherical droplet. I hope you like this explanation. Kindly like and subscribe and keep looking for more videos.